In the preceding lecture, we focused on the concept of phase stability and introduced the term coexistence curve to describe any set of temperature and pressure corresponding to an equilibrium between two phases. In this lecture, we provide further details on the meaning of coexistence curves, emphasizing the concept of dynamic equilibrium and reversibility. Starting with the second law of thermodynamics for reversible processes, we then give a detailed derivation of the three equations relating pressure to temperature for the solid-liquid, liquid-vapor, and solid-vapor physical equilibria. We then examine the phase diagram of water and explain why it differs in some respect from that observed for other substances. When we examine a phase diagram and imagine a heating experiment under a constant pressure, such as P1, we recognize that the system can take up to 5 macroscopically different physical states. At the lowest temperatures, such as at temperature T3, the system will be in a solid state. At the highest temperatures, such as temperature T1, the system will be in the gas state. And at intermediate temperatures, for example at temperature T2, it will be in a liquid state. The other two states correspond to situations where the system is on phase boundaries or coexistence curves. At the melting or fusion temperature, T subfusion, there is a dynamic equilibrium between the solid and the liquid phases. What we mean by dynamic equilibrium is a situation where the temperature and the pressure remain constant, while particles from the solid melt into the liquid, and simultaneously, and at the same rate, particles crystallize from the liquid state. In a dynamic equilibrium situation, there is no macroscopic or net change in the amount of crystal and liquid phases. But particles move from one phase into the other in both directions at the same rate. To increase the amount of crystal phase would require to remove some heat from the system. Conversely, to increase the extent of the liquid phase would require to transfer some heat into the system. At the boiling temperature, there is a similar dynamic equilibrium between the liquid and the vapor phases. The relative amount of liquid and vapor phases can only change when heat is either transferred into the system, hence increasing the amount of vapor, or transferred into the surroundings, hence increasing the amount of liquid. Over the next 3 slides, we will discuss the changing meaning of pressure when we consider the solid vapor, liquid vapor, and solid-liquid equilibria.